Okay, so today is the day that AP Chemistry gets challenging. If you take a little look-see here at the slides, looks like I left it kind of in the middle there. There's 121 slides for 8.4, okay? And this actually, we'll do it quickly in reverse. Sorry about this. All right, so we will start real quickly with defining how these reactions come into play. You know how the chapter 4 or unit 4 on chemical reactions was quite challenging, and these last couple of chapters with equilibrium and acids and bases have been challenging, and this kind of wraps it all into one fun little type of problem. So being how we have 121 slides to go through, I think we'll probably want to break this one up in a little bit into chunks. Okay, we start with the easiest one, which is a strong base reaction, and then we go into weak acid and strong base, which is much more challenging. I think there's like 6 example problems that they do that walk you through the patterns there. And of course, strong acid and weak base would then be equally as challenging. And weak, that's beyond the scope of this course. We're going to dabble in that a little bit, but that gets into some really a little higher level math that we aren't going to explore that. We're definitely going to talk about it and give you some of the easier examples, but we'll start with strong and strong. So if you're looking at these problems and you want to be able to talk about how this occurs and how these reactions take place, you're going to want to recognize, if it's a strong or a weak base. These reactions, you probably knew this term. Certainly we covered that in general chemistry, just real briefly. We said acid, base, salt, water. Boom. That's pretty much what we did. Now, a strong acid or base, your EQ is going to be greater than 1, which means it's going to go to completion, so you have the straight arrow. And if you throw in a weak, the equilibrium constant is going to be less than 1, and we'll have the double arrows, and that just by its nature is going to complicate things a little bit. Okay, so let's start with strong acid, strong base. What's cool about this is they'll go to completion, and you have those hydrogen ions. That's as strong as it gets, we said, and the hydroxide ions as strong as it gets. And we know that the Kw will be 1 times 10 to the minus 14th. One of the things that you might want to highlight on this page is looking for spectator ions. So that goes back to Unit 4 when we did the net ionic equation. So if you were going to start talking about this, this is usually the simplest example they give in general chemistry. In my first year chemistry class, we just say hydrochloric acid, keep it all together nice and happy, keep the NaOH as if it was one species when in fact it is not. And you put those two things together and you get salt and water. It's just kind of, that's just a nice little double switcheroo. But we know much better than that now, don't we? That this hydrogen chloride, especially since it's strong, is going to dissociate and you're going to have some hydrogen ions, chloride ions, and NaOH is soluble, and also a strong base, so that'll drive that into dissociating. So basically, you got 4 ions sitting there in solution, and what happens is 2 of them will combine to form the water, and 2 will combine to form the salt, the NaCl. But remember, the NaCl, that's the same thing on both sides, okay? And it's a chloride ion. So those are spectator ions. They got nothing to do with this. However, the H plus and the OH minus making water, now we're talking. So when you have a strong acid and a strong base, the net ionic reaction for that is hydrogen ion plus OH gives you H2O. Well, that's acid base chemistry 101, right? You got your acid and your base forming to neutralize and form the water. So that's the business part of this reaction, and that's in fact how they neutralize each other. All right. In this second reaction, by the way, you should be comfortable with this. It's just saying, well, what if this hydrogen attaches to water, which again, this is the reality, and this is a little cleaner and I think easier to understand. All right. You're actually taking H3O plus an OH minus and making 2 water molecules, but same thing, right? Okay. So let's go ahead and give this a go here. So we've done our job of finding the net ionic equation, but now we have to find which one of those, because we didn't add equal amounts. They never said in this problem that you added just as many H plus ions as you have OH minus ions. So one of those is going to be in excess. If hydrogen, H plus, is in excess, then it's going to be acidic. If the OH minus is in excess, then it's going to be basic. So again, we're looking at an equation like this, and you're like, well, I've got different volumes and different concentrations. Well, you remember from just doing this last unit, the goal is the mole. If we talk about moles of these things, then we know what there's more of and what there's less of. These numbers don't work. These numbers don't work. But combined, when you take the volume, use the molarity again as a conversion unit to convert it into moles, we can see that hydrogen's winning. If you were to use this, you would have thought OH was winning because it's a stronger concentration. But in fact, when you take the different volume into account, there's more of this. So it ends up having a greater amount of H plus ions. Okay? So as a result of that, that will be in excess. And then you can just do this little problem right here. You take these two numbers and just subtract them. And that's how many moles of H plus you'll have. Because all the other ones are neutralized by the OH minus. So 0.075 moles of these hydrogens are neutralized. And then you got some left over, which is 0.88 minus 0.75. So you crunch those numbers and then remember to do the total volume, because they didn't say it in this problem, but the volume's being additive. And you 250 plus 150 on the bottom there, and they're converted into liters. So you end up with, now you have the concentration of the hydrogen ion. Okay, so we're getting there because we got our equation written. We did this simple math to find out which one was in excess. And now, since we have the hydrogen ion concentration, we can do the last step, which of course, negative log of the hydrogen ion concentration is equal to the pH of 1.48, 2 sig figs. in the answer for the pH. All right. So you had a really strong acid and a really strong base. That makes a very good fight. And to a certain point, they're just back and forth and back and forth. But then all of a sudden, somebody's in a little better shape. There's a little bit more of them in the battle, however you want to look at that. And then the hydrogen ions ended up winning, which is not always going to be the case. You could have a relatively high pH and have the OH win this battle. Okay, so that is an example of strong acid, strong base. So that's the easy one. That's a piece of cake. All right. So if we were talking about weak acid, strong base, here's the thing. So you have a weak acid. I'm going to use this salt shaker since we were just talking about salt. This is going to represent a hydrogen. Okay. So a weak acid doesn't want to give the salt to anyone. No, I don't. I'm a weak acid. I like this hydrogen. I'm going to keep it. And then along comes big old mean OH, who's like, I'll be taking that salt. And there's nothing the poor little weak acid can do about it. So I really like that term. The OH rips that hydrogen right off of there and say, that's my hydrogen. You had my hydrogen. I'm going to take it away from you. You weak little acid, because I'm strong. Okay, you get the idea? All right. And then you're going to have water and a conjugate base of that weak acid, which will be a relatively strong base because it was a weak acid, and then you get a strong conjugate base. So here we go. A lot of times people will see this problem and go, ooh, yes, it's a strong, because you got KOH and HNO3. Whoops, it's HNO2. Weak acid. So that means we got to think. But the first part of this is not bad. Because if we look and we're going to write the net ionic equation, we know this is weak. So if it's weak, it's not going to, remember, it wants to keep the hydrogen. See, he's still got the salt shaker. He's like, HNO3. I like it. And then along comes, this is the story, along comes the OH, and like we said, so poor little HNO2 becomes H2 because the OH ripped that hydrogen off, and now you got the weak acid was forced to give up its hydrogen, and ends up being NO2 minus. All right. So now here's a really good question. Identify the aqueous species that have the highest concentrations at equilibrium. All right. So when this system achieves equilibrium, which it will, actually, right now, add the double arrow in your notes on there, because this is an equilibrium system. We don't know, what these concentrations are, and also it does go in the other direction to a certain point. Okay, but the strong base will kind of be that driving force, as long as there's hydrogens available for it to rip away, and if there are OH minus ions there, they will do that. So we're asking, what two things have the highest concentrations? So I want you, there are two of them. I want you to pause and think about it and see if you can tell me the whole shooting match, the whole problem. That's a hint I'll give you. Hit the pause and see if you can guess what they are. Okay. Did you pause? Okay. Because I'm going to make you think about it. Because the answer is not going to be given until the next lecture. That's how we will start the next lecture. All right. Bye.